Hi and welcome to section 5.5. The first video, this is the first video of two videos for this section. This is the last section that we'll be covering for Math 181. So we've been doing integrals the last couple sections of the book here, and they've been pretty straightforward. As you guys know by now, that's not the way math works. Unfortunately, nothing is ever straightforward. It's always the more complicated types of integrals that you get. And when you have those more complicated integrals, you'll often be using what's known as a substitution rule in order to help simplify the process. And that's what section 5.5 is all about, which is, as I said, substitution rule. And what this says is the following. If u is equal to some function g of x, if this function is a differentiable function, so if we can take the derivative, whose range is in the interval I and f is continuous on I, then the integral of f evaluated at g of x, whatever that function is, so f of u realistically, times g prime of x dx, this whole thing can just be simplified into f of u du. What does all this mean? Well, we're going to see. It's essentially, we're trying to play a game here of matching up whatever we start with into a much more simplified integral that we can take the antiderivative of. So let's look at an example. Let's say we want to find the integral of x to the third times cosine of x to the fourth plus 2 dx. Well, you can see this would be pretty messy. So we want to know, can we define u as some function, g of x, that when we take the derivative, we now have all the pieces we need to rewrite the original as a much more simplified integral. And this is where the game kind of comes in. Picking out the right function value for u. Often it's going to be the value inside the trig function or underneath a radical. Maybe exponents. If we have an exponent, we might be able to set that as our u value. So in this case, and then sometimes too, you can sort of guess ahead, because what are we going to do? We're going to want to take the derivative and end up with other pieces that are in there. So I have an x to the third and I have an x to the fourth. Well, I know what? I know if I take the derivative of x to the fourth, it's going to give me something x to the third, which leaves me another piece of what my original equation is. So I'm going to say let u equal x to the fourth plus 2. And again, I'm including that plus 2 because I want everything inside of there, because later on, I essentially want to find some simplified function. So if I just said u is x to the fourth, now I have cosine of u plus 2, and it's still a messy function for me. So if I say u is x to the fourth, that means what? The derivative of u with respect to x is what? 4x to the third dx. So now what I want to know is, can I write my original function as a combination of this u and the du dx to get a much more simplified integral. Well, what do I have here? I have this part, which I'll be able to substitute into there. And what do I have left? I have x to the third dx. Well, here I have 4x to the third dx. So I have to do what? If I divide everything by 4, I get what? I get 1/4 du, this cancels out, is equal to x to the third dx. So now if I actually substitute back all the pieces that I can, I have cosine of x to the fourth plus 2, so that's cosine of u. And then my x to the third dx is really what? It's 1/4 du. And so with my integral rules, I can do what? I can pull this 1/4 out. So this is really 1/4 integral cosine of u du, which is now a much more simple function to take the integral of, as opposed to the very messy one that we started with. And the game, as I said, really comes in here, trying to figure out what pieces do I have, x to the third dx, and how do I get just that by moving other pieces around, and what am I left with that I have to substitute in later. So this then becomes what? This is 1/4. The integral of cosine is what? Well, what do I take the derivative of to get cosine? It's sine. So sine of u. And so now this is what? This is an indefinite integral. So that means I have to have plus c, because maybe there was some other value there that I have to account for. So that's my integral, but now I have to go back. I wasn't trying to find some integral with u, I was trying to find an integral with x. So I have to go back and plug in my x values for u, so I get 1/4 sine of x to the fourth plus 2 plus c. So that's it. That's my integral there. Is there a way to know if I'm right? Sure. Take the derivative of this, right? So if you are on your final exam, or an in-class exam, depending if you have one before the final, don't just turn in the exam and say, God, I hope I'm right. I hope I had a good day here and I got the calculations correct. If you have the time, take the derivative of this. You can do that. You should end up with this as your answer if you take the derivative of that. And that's how you know if you've done the right work, done the right substitutions. So let's look at another example. Let's say we want to find the integral of the square root of 2x plus 1 dx. Well, as I told you, and I'll be honest with you, the way to get good at these is doing a bunch of examples. I don't know how many problems there are in your homework set, but if you do the homework and you're still not like, oh, I'm really good at these substitutions, I would go back and do some more. Go to the book and pick out the odd ones. Pick out the even ones. Give those a try. I know the answers aren't in the back of the book, but maybe if somebody else is doing them as well, you can compare answers. Did you get the same thing? And realistically, you can check your answers anyhow. Why? Just take the derivative. If you get the same thing back, you know you're doing it right. But as I said, you'll start to see patterns develop. Set what's inside the parentheses equal to your u. Set what's underneath the derivative, underneath the radical equal to u. So I'm going to say let u equal 2x plus 1. So that means what? du is equal to 2 dx. So I can plug this under here, so that's going to give me square root of u, and all I have left is dx. So I have to get rid of the 2 on this side, divide by 2, so I have 1/2 du is equal to dx. So now if I rewrite the original, it's the integral square root of u, and then dx is what? It's 1/2 du, so 1/2 du, which again, if I bring the half out, square root of u is u to the 1/2 power. And I'm doing that so that when I take the antiderivative, it's easier to figure out the numbers. Du. So this is what? This is 1/2. So for this one, the antiderivative, I'm going to add 1 to the exponent, so that's u to the 3/2, and then divide 1 over 3/2. 1 over 3/2 is the same thing as 2 over 3. So 1 over 3/2, keep, change, flip is 1 times 2 over 3, which is 2/3. And again, plus c. The 2's cancel out, so I get 1/3 u to the 3/2 power plus c. And now if I plug back in my x piece, it's 1/3 2x plus 1 to the 3/2 power plus c. So that's my integral. The integral of this is that value there. Let's look at one more example. That'll wrap up this first video. Let's say we want to find the integral of e to the 5x dx. And the reason we're doing all these substitutions is why? The chain rule, right? So if I was just to take the derivative of this piece, I'm going to have to do the chain rule with what's inside, and that's what gets me these other values that I have to account for, like the 1/2 du or the 2 dx. So same idea here. If I just was trying to do the integral of e to the 5x, I have to worry about what does the chain rule do to that exponent piece. So I'm going to make it easy on myself. I'm just going to say let u equal the exponent part, 5x, the piece that I would do the chain rule on. Same thing here. What would I do the chain rule on? The 2x plus 1. With the other example, the cosine example, what would I have done the chain rule on? The piece inside my cosine function. So again, those are other keys to try to figure out what do I want to use as my u value. Ask yourself, what would I have to use the chain rule on? So that means what? du is equal to 5 dx. I don't have 5 dx, I just have dx, so that means 1/5 du is equal to dx. Now rewrite the original. So I have e to the 5x, so that's e to the u. And then dx is 1/5 du. Take the 1/5 out if you want. Integral of e to the u du. And integral of e to the u is what? It's just e to the u. So it's 1/5 e to the u plus c. So now plug back in your substitution. 1/5 e to the 5x plus c. And again, if you need to, just check your answer, take the derivative. Well, derivative of c, that's gone. 1/5 times e to the 5x, well, derivative of e to the 5x is e to the 5x times the derivative of 5x, which is 5. 5 times 1/5 is 1, so I'm just left with e to the 5x. And again, that's how you can check your answers on these. So that's it. That's the idea behind substitution. Come on back, we'll see it as an application on a definite integral, and that'll wrap up our video series.